welcome everybody for the webinar of today. The talk of today will be given by Björn Hof, and the topic is elasto-inertial turbulence. So as usually, I introduce the speaker for a minute and then I leave him the floor. Björn Hof obtained his PhD in 2001 from University of Manchester in UK. From 2003 to 2005, he was research associate at Delft University of Technology, the Netherlands, and from 2005 to 2007, lecturer at University of Manchester. From 2007 to 2013, Björn Hof was the leader of a research group at Max Planck Institute for Dynamics and Self-Organization in Göttingen, Germany. Since 2007, he is professor at the Institute of Science and Technology, Austria, and among his several rewards, he received the RC UK Fellowship in 2005, the Dr. Meyer Struckman Science Prize in 2011. He has been granted of an ERC Consolidator grant in 2012, has been elected Fellow of American Physical Society in 2017, and he is recipient of the Siemens Foundation grant in 2019. So it's with great pleasure that I introduce Björn Hof for his webinar of today. Björn, I stop sharing and I leave you the floor.
Okay, thanks a lot, Francesco, and it's my pleasure and honor to be allowed to present in your seminar. So can you see the? Yes,
we see the presentation.
Okay, so yes, actually I haven't given this talk for quite a while, so I hope I get into it more or less straight away. But before I start, let me acknowledge a number of people who have worked in this problem in my group, and this is starting with Devani and Samantha, who did his PhD a while back. He is now a professor in India. Then George Chouhiri, who until recently was a postdoc in my group, also worked on experiments. He is now in the US faculty, and Jose Lopez, who recently moved to UPC in Barcelona. He worked on numerical simulations, and people who still work in my group on experiments are Atul Varshney and Sarath Suresh. Okay, so with that, let's get to the topic straight away. So if you add, this has been known for a long time, so if you add small amounts of polymers to a Newtonian fluid, Newtonian solvent, you can reduce the drag in pipelines, for instance, by very substantial amounts. You know, the ideal conditions can go up to 80% or so. And if you look here at this friction factor plot, I hope you can see my pointer, my mouse, then this is friction factor in pipes as a function of Reynolds number, and this is taken from Burke's paper in 1970. What you see here is the Prandtl-Karman friction factor for Newtonian turbulence and Hagen-Poiseuille law for laminar pipe flow. And right here in the middle, there's another line indicated where all the data accumulates, and this data has been taken from different experiments using different polymers, different polymer concentrations, and they all collapse on one curve, and this is the limit of high polymer concentrations. So as you start off with a Newtonian turbulent flow, and increase, you keep adding polymers, your drag is reduced and keeps going down until at some point it gets stuck on what is called also the maximum drag reduction asymptote. And if you keep adding more, it won't help you. You typically don't go beyond this point. Okay. So that is kind of the upper limit of what you can achieve with polymers in terms of drag reduction. And I already said it's independent of the type of polymer used. Okay. So now about this drag reduction phenomenon, you can take a number. There's a number of interesting open questions, and the first obvious one probably is the mechanism underlying polymer drag reduction. About this one, I will not say anything. So there are theories going back to Lumley about being basically a viscous effect or competing by Tabo and Dejean, also many years ago as viscoelastic effect. So, but what I will talk about for sure, and this is how I started to get interested in the problem, is the effect of polymers on transition. And if you look in the literature, and I just put a few papers here. So you will find both answers. One that says, well, transition is delayed, for instance, in Draht, Koiken, Newstad, and others. There's a number of quite early studies that actually say the opposite, that the transition happens earlier, and some early turbulence has been reported in these studies. So that was one of our motivations to try to figure out what is really going on in polymer flows. And another one is motivated by the slide we saw previously, this nature of this maximum drag reduction asymptote. Why can't you achieve drag below or reduce the drag beyond this asymptote, and what is the nature of it and where does it come from? And there's a number of different theories over the years, and typically, at least all the traditional ones, agree that the maximum drag reduction state is a marginal state of turbulence. So you reduce the activity of turbulence until you get to this minimum kind of, or edge, sometimes called edge state, and speculated to be related to the Newtonian turbulence edge state, where you then get stuck and you cannot go beyond. But it doesn't explain why you cannot go beyond. And in connection with this, so by Graham's group, basically, there was this proposition that it's a switching between active and hibernating phases in the flow. Okay, so that is the second topic I will address. And with that, let me give a little bit of a background in Newtonian pipe flow, which we need to see the differences in the transition encountered once we add polymers. So what you see here in a pipe, and I've taken pictures that many of you have probably seen many times. So these are the classic experiments by Osborne Reynolds. On the left, you see a pipe where he injected dye in the inlet, and at low Reynolds numbers, everything is laminar. The dye streak goes just through, doesn't mix. And as you increase, and this is the important point, at some point you get into a regime where you have spatial temporally intermittent structures. You have turbulence in some regions and laminar flow in between, and these pipes are traditionally nowadays called puffs of turbulence. And this is one of the signatures we are going to use to determine if we are in this Newtonian type turbulence regime. Yeah, as you go to higher Reynolds numbers, of course, at some stage, the flow becomes fully turbulent. So special thing about pipe flow then, of course, otherwise we wouldn't have this spatial temporal intermittent state, is that the laminar flow is actually linearly stable. So you need finite amplitude perturbations that then locally can create these turbulent structures, turbulent puffs. And yeah, we can look at this video here. This is what you would typically encounter at transition in pipe flow. These are puffs going by, and in between you have laminar regions. Okay. So how we started out on this, that was the PhD of Devranyan Samanta. He actually investigated now lifetimes of these turbulent puffs. What I didn't mention is that these turbulent puffs are transient, and I show this in a movie here for Newtonian pipe flow again, where we are in a co-moving frame. It's a DNS. We just look at a cross-section of a pipe and visualize streamwise vorticity. So you see this puff lives happily until around about now. It quickly decays, and this actually is a very clear signature of of Newtonian turbulence, which you can very nicely quantify. So if you are at a given Reynolds number and you have a straight pipe with a Newtonian fluid, and you add puffs at some point and you measure some distance away, you know exactly what percentage of these puffs should survive over that distance. So that you can find in DNS and experiments, and they all agree on that. So it's a very nice way of characterizing your flow. If you didn't know the Reynolds number, you know, just determining the probability, you could determine what your Reynolds number is. So and this now shows the probability of puffs to survive. So if you think about, so this is a Newtonian turbulence case. It's here. So at low Reynolds numbers, most of them die out. So below 1800, there's actually a negligible probability that puffs survive to the end of the pipe. Of course, this depends on how long my pipe is, but this is for the pipe lengths we had in this study. And if you ask me now how long it was, I would have to pass and look up in the paper, but it's a few hundred diameters. Let's call it 400 diameters. It's around that. So, and as you increase the Reynolds number, it becomes more and more likely that puffs survive until, you know, if you're at Reynolds number 2000, almost all of them will survive. Not entirely all of them, but almost all of them. And you have this S-shaped curve in between. So that is what happens in Newtonian flow. Now, if we increase the polymer concentration in our fluid from 0 up, then what you see nicely is that we still have this sort of S-shaped curve. So, but puffs are delayed clearly. So transition is delayed, and you have to go to larger Reynolds number to get the same percentage of puffs surviving over this distance in your pipe. So if you look at the 50% survival probability, you know, for 50 parts per million, so these are the concentrations, and we use polyacrylamide with a chain length of 5 million in this case, then, you know, you have to go to higher and higher Reynolds numbers with larger concentrations. So transition is clearly delayed, so that we thought, you know, it's a very clear-cut answer. But things are really a little bit more complicated than that. Otherwise, it would probably also be quite a boring talk. So if you now measure in the pipe rather than at the point the pressure recording, which we did before, we now measure the drag basically over some length of the pipe. And we do this again for different Reynolds numbers. So basically determining the friction factor. Okay, here the length is given, so that's over a distance of 300 diameters in this case. Then in the Newtonian case, well, it depends on the inlet conditions or initial conditions, if you wish. If our pipe is not perturbed, we can keep flows laminar up to quite reasonably high. I mean, for this pipe, somewhere around 6,000 or so in Reynolds number. And only after that, turbulence will arise. So in this case, in the form of slugs already, because these are high Reynolds numbers. But if you look down here, if we add perturbations, the first point where we can create turbulence that is you know, sufficiently long-lived and where we see an increase in friction factor is then a little bit above or around 2000, and then we basically have this hysteresis curve. So if we add perturbations, we approach then the Blasius friction scaling, and if we don't, we stay on the Hagen-Poiseuille laminar case. I hope this is clear. If something is not clear, please interrupt me at any point. All right, so now what happens if we add polymers? So we now take the 100 parts per million case of this polyacrylamide. What you see are two things. So the black data is similar to what we just saw, just in a pipe of slightly different diameter, but nevertheless, the first thing is, you know, for these open symbols, we add perturbations. So we cannot create puffs at the same Reynolds numbers where we were successful doing so in the Newtonian case, the black data. In the red data, this is delayed, which is fully in line with what I said before about lifetimes. So puffs are delayed to higher Reynolds. So that is the first point we already knew about. But the second point then is that whereas in the Newtonian case, our pipe without perturbation so the full symbols now, the solid symbols, remained laminar up to around about 6,000, and only then turbulence arose. In the non-Newtonian case, with the same pipe, same inlet, everything the same, no perturbation added, we cannot keep it laminar, but on its own accounts, turbulence will happen earlier in the polymer case. So round about, I don't know, Reynolds number 3000 or a little bit above, we cannot hold the flow laminar. So we still have this hysteresis loop, but it's also a lot smaller. So it's not only being delayed, but it's also shrinking from the other side. And of course, in terms of drag, the drag is reduced. So we are not going to the Brandt Kalman or Blasius curve, but we stay below in our figure. So that was expected. Okay, so if we push this now quite a bit further and we go to 500 ppm, so much larger concentration, it becomes even more interesting in that we don't have any hysteresis loop anymore. So the unperturbed and perturbed case are now shown in red and blue. But yeah, it doesn't matter at all if we add a perturbation. And if we look closely, now friction factor is not the best measure, but if we look closely, there are already deviations slightly above the Hagen-Poiseuille curve. Certainly, round about Reynolds number 2000 for sure. You can see it on here below that. It's hard to spot, and our resolution is probably not high enough for the measurements. But you then smoothly go. I mean, you don't overshoot. You don't approach towards the max towards the Newtonian turbulence case, the Blasius scaling, but you smoothly appear to go to this maximum drag reduction asymptote, and in both cases, in perturbed and unperturbed. And if we look at fluctuations, in this case in pressure, but you can also look at velocity fluctuations, which we did later on, PRV, LDV, it really doesn't matter. Pressure is just easier to measure. So it's kind of a point measure. We have a sensor that locally measures the pressure in the channel. Then what you see is that fluctuations arise much earlier than what we could spot here on the left, namely already below Reynolds number 1000, so far below where we can have Newtonian turbulence. And also these fluctuations, I don't know if I have oh yeah, I have it here. So in the Newtonian case, we have these distinct puffs, right, where we have the intermittency, spatial intermittency with laminar patches in between, and then another puff, laminar, and another puff. You see these dips in this case for velocity, URMS, but as I said, with pressure, it's the same. In the polymer case, you see fluctuations all over the place, and it's far less intermittent in space. So it appears to be a spatially much more homogeneous flow. And this is really sort of reminiscent to the studies I briefly mentioned earlier that reported this early turbulence state, where they claim transition actually happened earlier rather than later if you add polymers by these people here. And this then, kept us busy for quite some time to make sense of these two different observations. On the one hand, transition in terms of puff is obviously delayed, but then you get something else at much lower Reynolds numbers. So, and if we map out now our stability curve in our parameter space, so polymer concentration versus Reynolds numbers, and this is not the same as the Samantha data, but here it's different types of polymers, longer chains. So don't worry, the numbers are lower now because the molecular weights are much larger for this case. So this is actually a bit quite but we have a very similar plot in the Samantha paper. So transition delay, what I mentioned based on lifetimes in terms of puffs and Newtonian type turbulence, but then you have this other state kicking in that we just saw here, determined by fluctuations in pressure and velocity. And this curve goes down as we increase the concentration. And we could follow this much further down if we wanted, and I will show later on cases where we go to Reynolds numbers of order 1 and still observe this fluctuating state, which we then named elasto-inertial turbulence, and I will try to characterize this from an experimental view. So this, just to put it visually, so this is what we know about Newtonian turbulence. You have spatial temporal intermittency. It can appear in forms of puffs. If you're a little bit larger in Reynolds numbers, you will get growing slugs. And when we found this in experiments and first presented at the APS meeting quite a number of years ago, I guess in 2012 or so, we ran into Yves Dubiev, who also gave a talk on the same subject from a numerical side, and he observed this new state of what he's viewing here as span-wise structure. So it's Q criterion in a channel where basically he finds these span-wise vortical structures, partially at least related to vortices. And we got together, checked agreement, and in the end wrote this nice paper jointly. So that was quite a nice to get Yves on board with that. And in experiments, however, it's much harder to visualize this state. I'll get back to that later on. And this was one of the challenges for quite some time, and still is, to try to get structural information from experiments. So now what we did a little bit afterwards in experiments is that we took cuts at constant Reynolds numbers going across and increasing the polymer concentration. And the first one I'm going to show is the one up here. And this is fully in line with the traditional picture of polymer drag reduction, where, as you remember from the beginning of my talk, the maximum drag reduction state was interpreted as the minimal state or some marginal state of Newtonian type turbulence. Okay. So what happens, at zero concentration of polymers? Of course, we are on the Blasius friction, so this friction factor Reynolds number on the Blasius curve, and we will now increase the polymer concentration. So you see the fluctuations from pressure next to it. So as we increase polymer concentration, the friction factor goes down. So we have obviously drag reduction, and then we approach with increasing polymer concentration, the maximum drag reduction asymptote, exactly what is expected, and the classic picture of polymer drag reduction. Okay, now we take the rather unusual route. So we stay below what we mapped out in our parameter space, this sort of cusp-like structures where these two types of instabilities intersect. We stay below this intersection point now, and go along here, starting again from 0 ppm polymer concentration. So initially we are the same starting point, Blasius friction factor. We go down, drag reduces, nothing too spectacular, drag reduces further. Now it becomes interesting because drag doesn't only reduce to MDR, but it goes further. So it doesn't go to what's supposed to be the maximum drag reduction, but it goes beyond that. And we fully relaminize. You also see it here. And in between, we had these spatial temporal intermittent structures at 8 ppm. Then we relaminize. And afterwards, if we increase further, the drag increases again. We get this low level of fluctuations, much more uniform in time and space. And we are back on the maximum drag reduction asymptote. So this now, whereas the previous example looked perfectly in line with the traditional picture, this one completely disagrees with the traditional picture, starting with, if the maximum drag reduction asymptote is a maximum drag reduction asymptote, you cannot go beyond it. But obviously, for this choice of parameters, we can. Okay. Now, the flow structures we observe I already indicated from the pressure signals, but this is now some PIV visualization, fully turbulent flow. Then you go to a state where you get localized patches of turbulence, puffs basically, you fully relaminize, and then you get much more elongated structures, and fluctuations set in on top of that as you keep increasing Weissenberg number or polymer concentration. So that's what you see when you do PIV And the larger Reynolds number case that we already had before, you don't see relaminarization anymore, but you go basically to the maximum drag reduction asymptote without overshooting. So based on this, our hypothesis then was that the maximum drag reduction is unrelated, or that the eventual state that one reaches is unrelated to Newtonian turbulence. Certainly in this case at lower Reynolds number, it should be quite apparent that if you fully relaminarize, you have a different type of instability, and then you only approach the state. So based on these observations, this is kind of the new interpretation we gave to the maximum drag reduction. We checked this also in direct numerical simulations. And here, let me just check how I'm doing on time. Sorry. Okay. Can you still see my slides? Or
yes.
Yeah. Okay. Good. Yeah. So we basically did the simulations in rather large domains, unlike previous studies which were done in minimal type flow units, like in Mike Graham's studies. And here the picture was quite different from previous simulations, but fully in line with our experiments. So if we pick similar Reynolds numbers, 3,500, and now we increase the Weissenberg number in these FINIP simulation, basically direct numerical simulation, using the FINIP model, then drag decreases, which is not shown here, but take my word for it, it does as we go up in Weissenberg number. And then the interesting part happens, that we go back from fully turbulent flow to spatial temporal intermittency, and we get, in this case, a slug type structure. You go a little bit higher in Weissenberg number, you get puffs, and even less puffs, and then you fully relaminarize as you hit a large enough Weissenberg number, until, now comes the even more interesting part, at somewhat higher Weissenberg numbers, this new type of structures appear, and you probably see that they are sort of in the azimuthal direction, so they have the same span-wise orientation as we saw from these channel flow simulations from Eves 2 we have earlier on. And this is exactly what happens then at higher Reynolds numbers. This fills everywhere, basically, and you get what we call elasto-inertial turbulence. Right. So we have exactly the same type of relaminarization scenario at low Reynolds numbers. It only tends to happen at not too high Reynolds, tends to work at not too high Reynolds numbers. At higher Reynolds numbers, you don't fully relaminarize. But this is to do with how our instabilities meet in our parameter space, right? If you're down below, you will relaminarize. If you're above, you don't. So back to where we were. So I wanted to mention briefly an analogy, different context, but yeah, I already mentioned, so the structures agree with the channel flow structures. There are other ways of diminishing turbulence, turbulence control mechanisms, which we played with, and one which is quite efficient is to flatten the velocity profile in the way indicated here by the red arrows in this red profile. We add a forcing term that in the laminar flow would act as shown here, and the forcing amplitude you can define by how much you reduce the centerline velocity, for instance. Okay, details don't matter too much. The point I want to get across, as you increase this forcing, the constant Reynolds number, what happens is very similar to what we just saw. You go from fully turbulent flow back to spatial temporal intermittency, back to puffs, and then you fully relaminarize. Of course, there's no other instability now which takes you back up, but my message is just, this, what we saw here up to this point here, was a relaminarization process. We find this in experiments and simulations for polymers. Okay, so now the rest of the talk, I want to say a little bit about what, from experiments, we can say about the EIT transition, also in terms of structures. And let me just introduce sort of the interpretations that are around in the field. And a number of studies, also the first ones by Eves and co-workers, indicated that this transition is clearly subcritical. So meaning that you should have hysteresis. However, in experiments, I showed the curves before, but I didn't point it out. In experiments, everything always looks continuous, and we could never find any hysteresis. So that is a little bit tricky. Also, our own simulations in pipes indicate a subcritical scenario. Rather recently, then, group from India, Garg et al. Had this very nice paper in PRL, and they found that there actually, despite previous claims to the opposite, that there actually is a linear instability for viscoelastic flows that results in an unstable mode and some particular structures that I'm going to get to on the next slides. Another interpretation, so this would indicate more a supercritical scenario. Another interpretation was connected to Tolmie and Schlichting waves in a channel, which would then be a different type of subcritical scenario. And the fourth one was connected to an older observation of a purely elastic turbulent state, going back to Victor Steinberg's group. And more recently, this was connected to subcritical. So in this, elastic turbulence arises supercritically if you have curved streamlines. However, in plane shear flows like our pipes, we don't have such curved streamlines. However, there was always sort of this possibility that this may then arise subcritically, this elastic turbulent state, and there are indications from Aratya's group that where they actually observed some nice subcritical instabilities in a channel setup. Okay, so these are different possibilities, and now I'm going to show what we observed quite recently. So as I already mentioned before, it's surprisingly difficult to resolve any structures in experiments, and we tried with PIV quite a lot until we got successful to some extent, at least, in the measurements of George Schwery, which are shown up here, and this is going down to very low Reynolds numbers. So this is for two different fluids. Both are reasonably close to onset. So here onset would be at Reynolds number 3 or so. In this case, I think Reynolds number 15 or 20 the onset was, so we're not quite as close to onset, but this is how close we could actually visualize something. And what you see in green and red are deviations from the mean velocity profile. So let's just call them streaks. And what I would like to point out is that you have these repeating structures which have sort of a chevron type shape pattern. And yeah, so we observed those, and we knew about the study of Shankar Subramanian group and their linear instability. However, we had no idea what the unstable mode looked like. So, before we wrote this up, I actually said then to George and to Jose, who was at the same time in my group, we should actually look what this linear prediction actually, what type of mode it is. And Jose then computed it, and we were quite positively surprised that it actually is quite reasonably similar to what we see in experiments. Still, there are quite some differences. So first of all, the structures in experiments are obviously not as clean. They're much more noisy, and also the flows tend to always fluctuate. So we don't have sort of this, should be a steady or a time periodic state. I think it's a Hopf bifurcation, but we have sort of broadband noise, and it always looks chaotic. And this is the closest we can go to onset. So at least with the measurement techniques we have at the moment, there's little we can do beyond that. So another point is that in simulations, you cannot, or in instability analysis, you cannot push much below Reynolds number 90 or so. I will show, I think, on the next slide. So the curves bend back up, and there's sort of a minimum Reynolds number range which you can approach, but certainly there's no linear instability predicted for Reynolds number 5. However, it still leaves the possibility that the instability is connected to this mode, but that it happens subcritically. And there's actually been a number of studies by Rich Percival and co-workers. Page 2 we have also on it, and then also by a group from Singapore quite recently, which do weekly nonlinear analysis and discuss possibilities of subcritical transition, and they again find very similar, or basically the same chevron. Okay, so if we look at fluctuation amplitudes in our case, everything still looks perfectly let's call it supercritical. So there is no hysteresis we can find close to onset, and with some kind of goodwill we can fit a square root to it. Nevertheless, these are fluctuations, so it's a fluctuating state. It's not a steady state. The flow is always mildly chaotic, which, as I already said, indicates that we have further bifurcations, further instabilities before we can, at the point we can observe, and which is suggestive that the whole stability is a little bit more complicated than just the linear instability and the supercritical scenario. So another indication for a subcritical scenario, these are our data points in black. This is what I mentioned before from the stability analysis. So these curves bend back upwards. So this is for two different viscosity ratios where you have sort of a minimum range. You can push this a little bit further down, but you won't get far below Reynolds number 100, whereas in experiments, we can easily push our instability to Reynolds number 3 or so, and you just saw the structure on the earlier slide that arises here. So this is actually the elasticity number, but yeah, anyway. Then what happens if we now push further away from the onset of instability is that, so we started with these chevron type structures, and you kind of still see them here in green and yellow a little bit. But what happens quite quickly after is that you get much stronger and more sort of localized, sharper streaks appearing sort of in the near wall region, and they have also a tendency to appear in pairs. And if you look at the URMS as a function of radius, what you see at the low Reynolds number close to onset, where we have the chevron modes, is that at the center you have the highest URMS, so we call this the center mode, whereas at larger Reynolds numbers, where the structures at the wall dominate everything in terms of amplitudes, you clearly have this wall type mode. So closer to the wall anyway, you have the peak and URMS. So that's what you see here. And what is interesting is that this is not only happening at these low Reynolds numbers, which are shown here. So this is actually below Reynolds number 1000. But if you compare it now to the maximum drag reduction asymptote at Reynolds number 10,000, so quite far above, you still have these pairs of streaks, and overall the structure hasn't changed all that much. So that indicates a little bit that maximum drag reduction visually is certainly like the elasto-inertial turbulent case at low Reynolds numbers. And to quantify this a little bit more, this is probably one of my last slides. Am I still okay on time, by the way, Francesco? Or?
Yes. You have like 10 minutes more if you want.
All right, I just need a couple more minutes, so we have more time for discussion then. So this is a rather recent result, where we had this probably already a year ago or so, but anyway, the spectra of elasto-inertial turbulence and MDR that we compare here. So taken with laser Doppler velocimetry and assisted also by PIV. So I just show some PIV snapshots to indicate what type of structures we see. So what I call now elasto-inertial turbulence, EIT, basically defined this by being below Reynolds number 2000, so in a regime where we couldn't possibly have any Newtonian type turbulence. But in the Newtonian case, we wouldn't see any puffs far below this value. So this clearly arises. All we see here, without any doubt, arises from the elasto-inertial instability. And for comparison, I put the Newtonian turbulence case at larger Reynolds numbers, indicating some -5/3 scaling, being well aware, we don't really have an inertial range at Reynolds number 11,000, but I just put this as a pointer, and just I'm more comparing the overall shape of the spectrum. I mean, the slope changes, but it changes very much in a different way from the EIT cases. So in elasto-inertial turbulence, going down to Reynolds 1,200 here, a little above, and then up to 1,900 or thereabouts, they all show a very nice power law of -3. And this is indicative, and one may want to speculate connections to elastic turbulence, which it's an interesting question, but I wouldn't have the answer to or couldn't say all that much about it. Main point I want to make, now we go to much larger Reynolds numbers. I think this one is repeated from there. The blue one corresponds to the purple one here, but all the other ones are far larger Reynolds number in a larger diameter pipe, where we push basically in all cases we have sufficient amounts of polymers to be safely on the maximum drag reduction asymptote in all these cases. And what I hope you see is that in all these cases we also have a nice clear -3 scaling of the spectra. Okay, so structures look similar. Spectra have a -3 slope on EIT as well as on MDR, and this is, at least from my point of view, quite indicative that MDR is at the very least, very closely related to elasto-inertial turbulence. One may speculate if there's still some Newtonian type structures surviving, or if eventually at adding more and more polymers in the asymptotic limit, you end up with just this elasto-inertial turbulent dynamics. All right. So we were actually beaten to it with these -3 scaling. So there was a PRL, nice PRL by guys from MIT, Yamani et al., just a few months ago, who announced that the -3 scaling is characteristic for elasto-inertial turbulence in a jet flow, because they don't have the MDR state, they don't have drag reduction there, so that's something we still have. Anyway, we would have also liked to make this claim that -3 scaling is characteristic for EIT. We knew that when this paper came out, but anyway, that's life. So I think with that, I'm ready to conclude. So what I hope I could convince you of, or at least get the message across, is that elasto-inertial instability happens at low Reynolds and high Weissenberg numbers, so very unusually low Reynolds numbers. You can push it to Reynolds numbers order 1, maybe even below that. We haven't certainly haven't tried to find the sort of lowest, but we also expand in this direction to see. The interesting part there is a possible connection to elastic turbulence, so turbulence without inertia. And then the other points, EIT arises from, as far as we understand it in experiments, from a mode that at least is very much similar to the one predicted by linear theory. And then another point, that MDR, despite the name, is not the maximum drag reduction you can achieve. At least in some parts of the parameter space, you can push drag reduction well beyond MDR and relaminarize And then only afterwards, sorry, you can push drag reaction below that. And only afterwards, this instability kicks in, which at least for these parameters, I hope makes quite clear that the asymptotic state that arises after it is distinct and disconnected from Newtonian turbulence, and it's not the marginal or edge state of Newtonian type. Then the last point I made is that EIT and MDR have same spectra and very similar structures. And overall, probably the message I want to get across is that our work, I hope, offers a different perspective where you can interpret polymer drag reduction, rather than looking at the detailed mechanism, which for sure is very interesting, but I have little to say about it. But a more general case is more approach is that it is or can be interpreted as a competition between two different dynamical states. So Newtonian turbulence on the one side and elasto-inertial turbulence on the other. Okay, I don't have more to say, and I'm happy to take questions. Thanks for your attention.
So thank you very much, Björn, for the presentation. I would say let's, as you just said, let's open the stage for questions, and whoever wants to ask a question can just feel free to unmute the mic and straight away ask your question.
Sure.
Let's see. You can also write in the chat just in case your mic is has some problems. I can read them I can report the questions from the chat. Maybe I can start with one. Yeah, so I had a question regarding the comparison between experiments and modeling. I mean, I'm not an experimentalist, so I'm more from the side of modeling, and I always ask myself the question when polymers are modeled. You kind of capture one part of the dynamics by using like, I don't know, a FNAP, a FNSCR, or Aldred B model or something like that, but you're missing another part. Like, for example, we capture the Weissenberg part, the Weissenberg part, like the retardation time and so on, but is it enough to describe the process? In the sense, I think you carry out like rheological measurements to understand if you have like a shear stress which is always proportional to the shear rate, or if you kind of have generalized non-Newtonian behaviors. How does this compare with the modeling, and what is the effect of such a sort of polymeric interaction on the flow?
Yeah, so regarding this comparison, I didn't talk about the characterization of the fluids, which we do, but it's first of all, it's tricky, and secondly, so to answer your question, things agree surprisingly well, at least from my point of view, qualitatively, but not necessarily quantitatively. And when it comes to the Weissenberg numbers, so here things happen. I don't know where did we include the Weissenberg number here. Well, it will be in the paper, but it depends now how in the experiments you measure your relaxation time. In our early experiments, we used this Kaber method. Gives a completely different Weissenberg number from a rheometer, and it is certainly not easy to then figure out which relaxation time one should actually take and compare. Although there, other people in the community can answer this much better than me, who are experts on this. But what seems quite clear to me is that, at least for the time being, we don't have quantitative agreement, but qualitatively, I'm quite surprised. I mean, in the initial simulations, when we wrote our first paper, and then we took Yves on board after seeing his very nice results. It was not at all clear that the structures that he finds, and this still is not clear, are how they relate to what we see in experiments. Of course, if you look at friction factors and so on in the scaling, so they match nicely, again, qualitatively, not quantitatively, but structurally, these span-wise vortices, we still haven't been able to visualize in experiments, for instance. So pictures like this, we don't have from experiments. Yeah. So I think there's still quite some room for improvements, but it is quite challenging from an experimental side. Resolving these very weak span-wise vortical structures appears beyond our capabilities at the moment. On the other hand, on the rheology side, there are certainly quantitative differences that need to be addressed in future.
Okay, thank you. Let's see if there is someone else who would like to ask a question.
Hi.
Thank you very much for a very nice talk, Björn. I found it very, very interesting. I was wondering, actually, especially about the conclusions when you say there that EIT was originated from this linear instability, and I was wondering if you were able to observe some kind of secondary instability of the chevron structures, or
yes. So, I mean, this is what we observe close to onset, right? And if we go a little bit further, we observe this change from the center mode to a wall mode. Okay. And what we also observe is not shown here, but this just appeared in PNIS a couple of weeks ago. So you can look it up. George Schwery is the first author. Is that the amplitudes? This would be relating to this figure here, where we close to onset, we see this, square root-like increase in fluctuation rates. They will pick up strongly as you go a little bit further. They will rise quite steeply at a sharper slope. When this wall mode, what we call wall mode, kicks in, you can sort of also see it here from the images that these near wall structures have much larger amplitudes, so they contribute much more also to fluctuation. So that's as much as I can say. So yes, we do believe there's certainly a mode change. We believe it's a secondary instability, but from experiments, it's hard to say more than that, at least at this stage in time. I hope, of course, that our computational and theoretical colleagues will look into this.
Right. Thank you very much.
Sure.
So any question? Go ahead.
So first of all, very interesting talk, and thank you. And I want to ask about the slide. If you can go back to the slide when you observe relaminarization by increasing polymer concentration. So
this one, for instance.
Yes, this one.
Also pick this one
yeah, maybe like previous one, because you can nicely here see. So basically you fixed Reynolds number, and you just increased from 0 to 5 to 10 just polymer concentration. But and so for example, for 10 ppm, you actually see full relaminarization, like laminar state.
But you can look at velocity profiles. It will be, Hagen-Poiseuille to, or we can say from, our PIV measurement, it's a parabola. But
Okay, so basically, depending on Reynolds number, you can find this concentration for which you have full relaminarization.
Yes.
And it will actually depend. So it will probably it will increase, like when you increase the Reynolds number.
So it only works in a certain regime. So it's a matter of where your two instabilities intersect. And this changes with pipe and polymers. So, you know, we've only explored this a little bit. In smaller diameter pipes, it tended to happen lower. We have a new case now, which is above 5,000, but I don't know how far this can be pushed. In a larger diameter pipe, we are now above 5,000. I don't know where exactly. We haven't mapped it out, but certainly we saw relaminarization at 5,000. So yeah, it depends exactly on how, I mean, we understand this curve here, but how this curve changes with polymer concentration and pipe diameter is now in reality the sort of shear stress, or at what Reynolds number you get what Weissenberg number, you know, that this you can determine by tuning the pipe diameter. In simulations that probably doesn't make sense, but in experiments it does. Yes, so if we knew how we can push around this curve, we could probably even get relaminarization at higher Reynolds numbers. But yeah, it only works if you stay below this intersection point here. If you're above, you know, you just go smoothly from one into the other regime, but there's no open space in between where you have this laminar flow here. So then you have to stay below this point, then you relaminarize. But yeah, that was, I don't know if that answers the question already, or
yeah.
Okay. Yeah.
So just a follow up. So if I understand it correctly, above the intersection between like Newtonian turbulence and elasto-inertial turbulence, if we move above of it, there must be like a kind of one can characterize how we transition from the Newtonian mechanism to the elasto-inertial mechanism, eventually including interaction between the two kinds of turbulences.
Well, so there then it becomes harder. So here it's simple, right? Because you relaminarize. So that is a nice thing about it, and you have a clear sort of dividing line between the two different states. If you're above, you see what everybody else saw in the past. You know, you simply go from turbulence and Blasius friction scaling here to the maximum drag reduction asymptote there, and then what you would have to do is look at structures, you know, and what is hidden behind these, what I have here in fluctuations. Then you would have to determine where do I still see the sort of Newtonian type self-sustaining cycle, up to what concentration, and here then at the eventual state, do I still see it, or do I only see the elasto-inertial turbulence self-sustaining cycle? But this, you know, is challenging, but I, you know, would be, I would think it's certainly worthwhile, and it would be great if somebody can figure this out. So that.
But I mean, I was just thinking to the like to the feature you showed before that seems to be preserved in terms of elastic turbulence, like the power law, like the scaling law -3, and this is not a feature which you should have for Newtonian flow. So, and maybe
exactly. So this is exactly what Sarah is supposed to do right now in the lab. Okay. He still sent me emails at 3 in the morning last night, giving me the figures for this talk. So that's good, but I'm not sure if he made it to the lab in time. I have to call him after the talk, chase him. Okay. But this is exactly, you know, we have this point here,
okay,
which is I jump to the slide in a moment, you know, which is sort of a Newtonian type spectra. As I said, it's not a big inertial range there, so -5/3 is a bit. But anyway, it's clearly what you get for Newtonian type turbulence, and we have the -3 scaling here. So I want him to fill in the gaps, the sort of blanks in between, and see how this progresses. So that is also something we can do. So this is relatively straightforward now for us to do. When it comes to, you know, a more detailed understanding of the underlying self-sustaining mechanism, this is, you know, even more challenging. But yeah, so that's what I mean. We have this one here. This is a Newtonian one. This would be Reynolds 11,000, and now the closest one here would be the green one, 14. We also have 10 or 12,000, one very close to that Reynolds number, and there it's clearly -3. So we have the extremes, and we can easily fill in the gaps in between. So in terms of spectra, yes, we can. That's in progress.
Yeah, and basically the point was the still open question is how much the near wall streaks influence the scaling, because basically near the walls your polymers will react differently than in the bulk. So more or less that's the kind of thing, right?
Yes, so you could look at the near wall cycle. I think this would be a very good starting point. Yeah.
Okay. Thanks. Let's see if there is someone else who would like to ask questions. Just once again, feel free to unmute your mic or write in the chat. Okay, so this doesn't seem to
maybe
be the case.
I can have a question actually.
Go ahead.
Yeah. I was wondering, you said that the limit between the laminar and the elastic turbulence, this curve you qualify for your case, but it varies with some parameters. And is it really sensible to the shape of the? I think that you work with a pipe, and what is the difference between the pipe and channel, for example? Does it make a difference?
Can you repeat for which curve? I was distracted for a second.
This spatial transition, you have the possibility to relaminarize.
Yeah.
And yeah.
So either we relaminarize or we don't. So basically it depends on
this
intersection here.
Yeah, this one. Yeah. So the red curve here. You said that this red curve, you don't know exactly how you could push it to the high Reynolds number. And what are the parameters that control this, let's say, this red curve? It could be also the shape, or does the pipe and the channel is different, for example?
So it should be the Weissenberg number, right? So I don't think any other geometrical things should really enter. But then by making the pipe diameter larger, let me get this right now. So then keeping the Reynolds number fixed, we have in a larger pipe, we have much lower wall shear stresses. That also means that the Weissenberg number at this Reynolds number will be much lower. And therefore, I would expect this curve to move up, But it tends to do that, but I don't think it moves as much as we would expect. But there may be some experimental errors, and you have to mix polymers, and polymer batches differ from time to time. So it's not so. It's also time consuming to do such a curve, and we haven't tried very hard, but we have a few data sets now for this is I think taken 10 or 8 mm pipe. We have a 4 mm pipe where the intersection between these two curves was around about 3,000. That's in the Samantha paper 2013. So that should be somewhere here around 3,000. And now we also have one in a 20 mm pipe, so basically twice the diameter of that one, where the intersection is somewhere above 5,000. So it goes in the right direction, but I wouldn't be entirely sure if it's not a little bit more complicated than just the Weissenberg number. I don't know, but yeah.
Okay. And maybe a very short question also. You said in one slide that it was difficult to measure to qualify the transition at very low Reynolds number. So is it experimentally that what is the main problem to qualify this transition of elasto-inertial turbulence at low Reynolds number?
So when it comes to structures, and again, you know, it may just be lucky that at someday we have, you know, nice conditions, the right amount of seeding particles, and the polymers are not degrading or whatever else may happen. But we cannot always visualize as close to the critical point as we would wish. And first of all, initially we also don't know what the critical point is. You have to think about we cannot just vary Reynolds numbers. At some point we can, but at some point our polymer fluid degrades. Then we have to mix again, or if we still have some over from the previous batch, we have to refill the pipe, and then we do sort of the new measurement with this new batch of fluid. And given sort of error margins for mixing these polymers, the critical point may shift by something. You know, we had it at 3 or so, and in the next run it may be at above 5 then, and then we do our measurement at 5 and we only see laminar flow, so it's not so straightforward to scan parameter space as in Newtonian fluids, simply because the fluid ages and you have to replace it. So this is quite a nuisance, and makes it then a bit matter of trial and error and a bit of luck involved if you could resolve something close enough to critical, or sometimes, you know, your images just simply are too noisy and then you have to repeat, and then your critical point shifted a little bit. Yeah, it's much more tedious than studies in Newtonian fluids.
Okay, thanks.
Sure.
Okay. So I think then we can close the webinar of today. I would like to thank Björn once again for giving the talk. It was very interesting, very clear, and it opened a number of questions and quite lively discussion. So thanks Björn for
thanks
the talk.
A lot, Francesco, and thanks to everybody, and to you, Francesco, a nice and safe stay at the DFT meeting.
Thank you.
Okay.
Thank you.
Then bye-bye.
Bye everybody.
Okay, bye-bye.